Hello human beings. I mean students. Welcome back to my channel, the Goddess of Econ. Today, I plan to cover what on earth is discounting. What on heaven and earth is discounting or discounting of cash flows? Let's take a short journey together to find out. My bad. Not this kind of discounting. The concept that I will cover today has nothing to do with shopping. Okay, suppose you have $1 in your pocket. If you don't have anywhere to spend this money, it will be better for you to deposit it in your bank account, rather than do nothing. Now, let's suppose that the 1-year time deposit interest rate is 10%. In this case, if you deposit $1 today in this deposit account, how much will the dollar become in 1 year's time? Well, it's very simple. It can be calculated as follows. $1 plus $1 times 10%, which equals $1.10. Simple, isn't it? So the principal plus the interest will be what you will receive next year. Now let's rewrite the equation above, replacing 10% with a letter R, which economists often use to denote the interest rate. This equation tells us that, in a year's time, $1 will become $1 plus $1 times R. This equation can be again rewritten as the following. $1 times 1 plus R. We can see that the number 1 in the parenthesis represents the principal itself, and R in the parenthesis represents the interest rate. So this formula shows how much you will receive in a year's time. And now, what if you put $100 in the bank account? How much will it grow to in 1 year? Well, $100 is just 100 times $1, isn't it? So it simply becomes 100 times 1 plus R. Now if we denote the amount invested, that is the principal amount, as N, we can generalize the equation as follows. If you put in N today, you will get N times 1 plus R in a year's time. Hope this is clear. Now let's say, after 1 year, suppose you redeposit all your money, that is both principal and interest, for 1 more year. How much will your money become in 2 years' time from today? For the sake of simplicity, let's just assume that R doesn't change over time and stays constant. Okay, after the first year, $1 becomes $1 times 1 plus R. And at that point, if you put that money back into the 1-year time deposit account, then it will further grow to $1 times 1 plus R times 1 plus R. Sounds confusing, but simply this means, in 2 years' time, $1 grows to $1 times 1 plus R to the power of 2. Not too difficult, is it? Similarly, in 3 years' time, $1 grows to $1 times 1 plus R, raised to the power of 3. So in t years' time, we can conjecture that $1 will grow to $1 times 1 plus R, to the power of t. Given this, if you deposit $100 for t years, then this grows to 100 times 1 plus R, raised to the power of t. So if you deposit amount N for t years, then you will get N times 1 plus R to the power of t, at the deposit maturity. Of course, this is under the assumption of annual compounding. That is, we have assumed that, every year not only your principal but also your interest will grow together at a rate of R. This concept is called annual compounding. So it can be said that, under annual compounding, your de facto principal is growing every year by the interest amount, N times R. Now, let's think of all this money-growing business in a completely reverse way. Suppose the time deposit interest rate, no matter how long the maturity is, simply R. If someone says he will give you an amount of it in 1 year's time, how much would this amount be actually worth from today's viewpoint? Let's consider a case where R equals 10%, and the amount equals $110. Then we know that, from the equation above, if we deposit $100 today, it will grow to exactly $110 in 1 year's time. Here, $100 can be interpreted as the present value of $110, which is the future value. Just for your information, the present value is often abbreviated as PV, while the future value is often abbreviated as FV. So far, so clear? Yes? Not really? Hope it's clear. Now we can rewrite these equations using present value, PV, and future value, FV, as follows. In t years' time, PV grows to PV times 1 plus R to the power of t, which then becomes FV. And from this equation, what do we need to do to get PV from FV? That is, to find PV when only given a FV? Well, we can just divide both sides by 1 plus R to the power of t. Then we have PV equals FV divided by 1 plus R to the power of T. In our previous example, FV was $110, and R was 10%, and T was simply 1. So, with regards to this specific case, the PV equation can be written as follows. This shows us that $110 you will receive in 1 year's time is worth exactly $100 today. That is, the value of $110 in the future is the same as the value of $100 today. In other words, you would be indifferent between receiving $100 today and receiving $110 a year later. Just to make sure that you guys grasp this backward idea completely, let's consider another example. If someone says he will give you $110 in 1 year's time, and $120 in 2 years' time, how much is this arrangement worth from today's viewpoint? Well, all you need to solve this problem is the following PV equation. Simple, isn't it? Once you have FV, you can convert it to PV using this equation. Now let's try that. First, $110 in 1 year's time is worth exactly $100 from the standpoint of today. Secondly, $120 in 2 years' time is also worth exactly $100 from today's standpoint, as the interest rate is 10% per annum. So the total present value of future cash flows turn out to be $200. Do you agree? Well, sorry guys. I have tricked you. This is a wrong answer. Due to compounding, $100 today will grow to $110 in 1 year, then $110 will grow to exactly $121, not $120 in 2 years. So the present value of $121 is exactly $100. This means the PV of $120 would be slightly less. So, how much is this worth today? It is worth about $99.17 today, according to the calculation using the PV formula. So in total, we can conclude that the future cash flows are worth $199.17 from today's standpoint. What we have done so far is neatly called discounting, or discounting of future cash flows. By the way, discounting is one of the most important concepts in finance or financial economics, so you students gotta get used to thinking backwards like what you have done today. In fact, finance is all about thinking backwards. So you'd better be prepared to do so. Lastly, let me point out that the interest rate is often called a discount rate as well, to emphasize the fact that it has been used in discounting future cash flows. Plus the whole thing that you multiply the FV by, that is 1 over 1 plus R to the power of T, is called the discount factor. So if you multiply FV by the discount factor, you can get the PV right away. Please do not confuse it with the discount rate, which is simply R. Hope you enjoyed today's lecture. Again, I'd like to say that thinking backwards is very important in understanding finance. And I hope you learned how to do it well through today's lecture. Please visit my channel often, as there's a lot more to come. May God bless you all.